I'm Claire Parkinson, a scientist at NASA's Goddard Space Flight Center, and this is the third of 3 videos on using math in some of our satellite data results, and in particular for sea ice. Now, in the first of the 3 videos, we came up with this plot of monthly average Arctic sea ice extents over the period of our satellite record, a particular record that starts with November of 1978 and goes through the end of December of 2012. This is a great plot. It's very helpful for a lot of things, but it doesn't tell us what's the change in the Arctic sea ice over this record. And so the confusing factor was the fact that the seasonal cycle, way more ice in the winter than in the summer, obscured the number of what's the change in the Arctic sea ice. And so in the second video, we took out the seasonal cycle by using yearly averages. This worked. We ended up getting a number. It was a good number. We used that number a lot. But it wasn't entirely satisfying because it lost a lot of information. In other words, for each year, instead of having 12 monthly averages, we only had 1 point, the yearly average. So a lot of information was lost. So in addition to taking the seasonal cycle out that way, we use a somewhat more sophisticated way to take it out. And so in this video, I'm going to show you the somewhat more sophisticated way. Since we're talking with math students here, then I thought it would be good to show you the somewhat more sophisticated way. Now we're going to retain the same number of points, but we're going to remove the seasonal cycle by, instead of plotting the first point, November of 1978, instead of plotting it like we do here as a monthly average, we're going to instead turn it into what's called a monthly deviation. And the way to do that is you compare November point, November ice extent for 1978, 11.782 million square kilometers, and you subtract the average of all the Novembers. I've highlighted in red here the Novembers. So we're no longer confusing November with December and January and February and March. We're only comparing November to November. And that's how we're removing the seasonal cycle. So with November, we subtract the average of all the Novembers, which came out to be 10.756 million square kilometers. You subtract those two, and you get 0.976 million square kilometers. And then you go ahead and plot that point. So now we're going to plot things, some of which are going to be positive, some of them are going to be negative, because some will be above the average and some below. So we've got a scale now that includes negative numbers. So we plot our first point. We move on to the next data point, which is December of 1978. We take December of 1978, and now we compare that only with all the other Decembers. So again, we're not comparing it with March and July or any other month, just December. And we subtract the average of all the Decembers. So all those points, average them out, and we get 12.839 million square kilometers. And we subtract, and we get 0.799 million square kilometers. We go ahead and we plot that point. And we proceed to do this and plot all the points. And this kind of, at first, looks like just a jumble of points. And so to make it look better and show more what we're trying to show here, we do connect the dots. We connect the dots so that now with the dots connected, it's much more clear what's happening to the time series. So this is the time series with the dots connected. Now we've got the same issue that we had in the second video, which is we still would like to get what's the way to get a number out to say how the Arctic sea ice cover has changed. We can see it's decreased, and we've got a lot more detail now about that decrease than in the yearly averages, which had only 1 point for each year. but we still would like to get a number. And so we're going to use the same method developed by Gauss and Legendre, the same method of least squares. So we're using the least squares method to get a line through those data points, and this is the least squares line through the monthly sea ice extent deviations. And now we take that line and do the same thing we did before with a line. Once you've got a line, you calculate the slope the same way. It doesn't matter whether the line represents monthly deviations or whether it represents sea ice extents or whether it represents something about your health or temperatures in the atmosphere, whatever. Once you've got the line, you can calculate the slope, and that's part of what's so powerful about learning math. You can use it in so many different ways. So now we've got a decrease from there down to there over the time period of, now it's 409 months, because now we're dealing with monthly deviations and no longer yearly averages. And the decrease is 1.874. So 1.874, and since it's a decrease, we put a negative sign. The slope is a negative 1.874 million square kilometers over 409 months. Do that division, divide 409 into this value, and you get a value of negative 4,582 kilometers squared per month. Multiplied by 12, since there are 12 months in a year, and you get negative 55,000 square kilometers per year. So that's the slope of the line, and so now we've got our result, negative 55,000 square kilometers per year. We've got our linear least squares line, and we've got these data points that give us a lot more details about what's happened over the course of that decrease than when we just had the yearly averages. So here we could see the yearly averages from the second video, and now the sea ice deviations from this third video. And we could see that these lines, they're slightly different slopes, but really close. So it's 55,100 square kilometers if you average the yearly data together, and 55,000 square kilometers per year if you do the monthly deviations instead. Both of these are very useful. Both of them are used a lot, and the yearly averages are often more useful for showing to a general public. The monthly deviations are often more useful for a scientist who wants more details about the changes in there. But they're both very useful, and you can see that the resulting change in Arctic sea ice comes out really close no matter which method you use. Antarctic, we do exactly the same thing, and again, that's the power of math. You learn mathematical techniques, and you can use the same technique over and over for different things. So again, to get our monthly deviations, we start with the first point, which is a November point, November 1978. So we highlight all the Novembers, take the average of all those Novembers, subtract the average from the point we're looking at, the 1978 point, do the subtraction, and now we get a slightly negative value, and we plot that slightly negative value there. We do the same thing for December, the second month on the plot, December of 1978, and now we compare it with all the other Decembers. So we're removing the seasonal cycle by comparing December only with December, comparing January only with January, and on. And we end up now, when we take the December value and we subtract from it the average December value, now we get a value that's very, very close to 0.004 million square kilometers. And we go ahead and we plot that point, and you can see it's very, very close to where the 0 is. And then we plot the whole set of points, and And this kind of plot, this kind of scatter plot, this is the kind of thing that sometimes people will look at and they'll say, oh, wow, I see like a person here. Here's somebody's head and legs, and maybe that's an arm and that's an arm. You know, you can see lots of things like that in this kind of scatter plot. But what we want is to see the sequence. And so therefore, we draw the lines in there because they take away that kind of picture of a man or a woman standing there, and instead you come up with what we're really looking at, which is the data points and the time series of the data points. So just by adding the connecting lines, we focus in on what we're really looking at. And then, once again, we've got our data points there, our connecting lines. We go to the method that Gauss and Legendre initially developed, the least squares method, initially developed for a very different set of problems that they were looking at, but has been expanded to widely used method in science, and in particular for finding least squares linear fits for a set of points. And so that's the line that you get if you do this method of linear least squares. Huge advantage being that everybody with those same points, if they don't make an error, gets the same line. So this is really important and good for scientists so that it can be reproduced. Your results can be reproduced by other people. Once we've got that line, and this line is from the previous slide, now we can calculate that the increase was 0.525 million square kilometers over a time frame of 409 months, the same time frame as for the Arctic, since we're using the same data set source. We divide the 0.535 by the 409 months, and we get 1,308 square kilometers increase for every month, and multiply by 12 to get 15,700 square kilometers per year increase. And then that allows us to put that number on our plot, which now has all our data points. It has the linear least squares line, and it's got the slope of that line. So that's the final result for the Antarctic, and you can compare it with the final result from the previous video where we were looking at yearly averages, and you can see that the monthly deviations have a lot more information in them, a lot more points retained, but the yearly averages, the result is very close. It's not as close as it was in the previous case, but it's pretty close. It's actually about 98% of difference between, they're within about 98% of each other. So, no matter which method you use, you get a curve that shows you what's happened to the Antarctic sea ice, and it's been increasing. And so now we've got the monthly for the Arctic, monthly for the Antarctic, monthly deviations in both cases, and we've got final values of decrease in the Arctic of quite a big amount, 55,000 square kilometers per year, and an increase in the Antarctic of a much lesser amount, but it's still very interesting to people who study climate that the two have different results in terms of one's decreasing and one's increasing. So it's a much smaller amount, only 15,700 square kilometers per year, but that's still noticeable. Now, I put this slide up just to let you know that we do update our results roughly every week. And so roughly every week, if you go to this website that's indicated down here at the bottom, if you go to that website, you'd be able to get updated results for both the Arctic and the Antarctic. And the plots that we put up several versions of plots, but this shows particular set from that. And you could see that up until January 26th of 2014. The Arctic in January was kind of low compared to the Arctic ice extent was kind of low compared to previous decades, whereas in the Antarctic it's high. In fact, it's above the averages for these previous decades. So we can, you can get updated results by going to that website. Also, in addition to doing these calculations for the entire Arctic and for the entire Antarctic, you can also look at individual regions. So we've got data available for the individual regions, and anybody who wants to can go in and do the same kinds of calculations, but for different regions. We've got 9 different regions in the Arctic, and we've got 5 different regions in the Antarctic. And we do the calculations on all and try to look at the differences that show up in different regions. And then this I just put up to get back to the fact that NASA scientists look at all sorts of different things. And this just happens to be 4 other plots that you can also look at and get like linear least squares lines through. And this happens to be ozone, the average area of the ozone hole. This is sea level changes. This is temperature changes in the upper portion of the atmosphere. It's actually the lower stratosphere, but the lower stratosphere is still high up in the atmosphere. And then, and where temperatures have actually decreased somewhat, and then the temperatures in the lower part of the atmosphere, more where we're familiar with, where we breathe, and also where airplanes are, and so the lower part of the atmosphere, called the troposphere, the temperatures have been increasing. Same mathematical techniques can be used for all sorts of different things, and these are areas in which NASA scientists use them in addition to all sorts of other things like carbon dioxide and sea surface phytoplankton and all sorts of things NASA scientists do it for. And then scientists around the world doing things in medicine, things in biology, things in chemistry, all can use the same kinds of math techniques that I've just shown you here in these 3 videos. So the math is so powerful. If you learn the math, then any science is going to be easier for you than if you don't learn the math. And the math really is fun to learn. So I really encourage enjoying the math and recognizing its power because of how valuable it can be.